Hi, my name is Axel Herzschuch, and I'm happy to present our paper Turbocharging SPJ Query Plans with Learned Physical Join Operator Selections. This is joint work with Claudio Hartmann, Dirk Habich, and Wolfgang Lehner. Our paper is about query optimization and, in particular, physical join operator selection for arbitrary select project join query pattern. Now, to understand our focus on operator selection, we first have to shed light on the operator selection quality for state-of-the-art systems. For instance, PostgreSQL, which follows a standard textbook approach where physical join operator selection and logical join ordering relies on cardinality estimates. On the left side, you see the join order benchmark execution time of a vanilla Postgres instance, and in particular, we found out that Postgres uses a balanced mixture of index-nested loop joins and hash joins to execute the native query plans. Now, to put the operator selection of the native plans into perspective, we restrict Postgres to execute the previous join orders with hash joins only. And as can be seen, the increased query response time of the hash join restricted plan equivalent indicates that Postgres does actually a decent job in selecting physical join operators. However, the question remains whether we can do even better. Therefore, in our third experiment, we exhaustively enumerated and executed all join operator combinations for the previous join orders. And as can be seen, selecting the single best physical join operator for each join reveals a huge potential for optimization. To lift this potential, we propose TONIC in our paper. And TONIC is a white box learning approach built on top of a generic query optimizer. And as will be shown during the presentation and in the paper, TONIC achieves close to optimal operator selections. The foundation of TONIC is the so-called case-based reasoning learning paradigm, or CBR in short. CBR is an established psychological theory in the field of human knowledge acquisition. And according to CBR, knowledge is organized in blueprints that are called cases. And cases are basically memorized problems and their solution. Now, the main workhorse of CBR is case reusing, where new problems are matched with known cases to generate new solutions. And these solutions are then refined by external feedback and stored as new cases in the case space. Next, we need to map the core principles of CBR to physical operator selection. And as can be seen, the core data structure that we need to implement, therefore, is the case base. As case base for TONIC, we introduce a new kind of synopsis, which we call Query Execution Plan Synopsis, or QEPS in short. The QEPS basically is a prefix tree of logical join orders, which allows us to share partial join orders across multiple plans. For instance, Plan 1 in this example joins R and S, while Plan 2 additionally joins U. And in this context, we consider Plan 1 as a prefix of Plan 2, as both share the same join of R and S. Now, the main trick is that we store a cost summary for different physical join operators at each node, which tells us the operator that is very likely to be the most cost-efficient operator for the next join along the prefix. For instance, here we see that CT stores join operator costs for joining T and S using a nested loop join or a hash join respectively. The sum within CT indicates that we consider the operator costs of all previous plans that match the abstract prefix. Also, this example only considers linear join paths for plans 1 to 4. The QEPS seamlessly integrates bushy join plans as well, as you can see in the paper. As for the operation mode of TONIC, we use the native optimizer of a DBMS to generate an initial query execution plan for the current query of our given workload. From the initial query execution plan, we retrieve the logical join order that is then matched against our QEPS to identify the longest prefix match. Afterward, we override the operator selection of the initial plan by reusing the learned operators for each join along the prefix match. The refined plan is then executed, and after query execution, we collect the true sizes of intermediate results. We use the actual cardinalities to derive very precise operator costs for different join implementations for the current query. And note that these cost predictions can be assumed to be very accurate, as we use actual cardinalities instead of error-prone estimates. And based on this cost feedback, we update the cost summary of each QPS node for existing prefixes and add new branches into the prefix tree if necessary to reflect the new join order. Now let's have an example to better understand the operation mode. Here we assume that we are given an empty prefix tree and the first query that joins R, S, T, and U. Since our QPS is empty at this point, all operators are selected according to the underlying optimizer and as there is no possible prefix match. However, after query execution, we use the actual cardinalities to derive the cost of all join operator alternatives. Accordingly, we add a new branch to the QPS to reflect the prefix RST and U and store all respective operator costs at each node. Based on this feedback, we see that a combination of nested loop join, hash join, and nested loop join would have been the most cost efficient for the given query. Now, as a second query, we again join R, S, T, and U, but with an additional filter condition on table S. Nevertheless, TONIC identifies a full prefix match and executes the query with the operator selection determined by the previous query. After query execution, TONIC recognizes that it actually would have been better to use an index nested loop join for joining T with its prefix due to the filter condition. To decide now whether to recommend an index nested loop join or hash join for future queries, we add the operator costs of the current query to the operator costs of the past queries. Therefore, by using the operator with minimal cumulative cost, we are very likely to select the most cost-efficient operator for future queries. Another option would be to introduce a more aggressive branching policy that introduces new prefixes for each individual filter condition. And of course, this more aggressive filter-aware branching policy that can be found in the paper heavily reduces conflicting operator decisions at each node. Now let's consider a third query which joins V and W to the existing prefix R and S. Since V and W have not yet been considered, TONIC again uses the native optimizer to decide for the operator selection for the join V and W. Nevertheless, the partial prefix match for R and S now allows TONIC to reuse past experience and recommend an appropriate operator for the first join. Now, after overviewing the main concept of TONIC, we want to evaluate some of TONIC's code characteristics next. As a performance overview, we show here the results of the join order benchmark where primary key and foreign key indices are provided. We compare the standard Postgres optimizer with and without TONIC and distinguish two scenarios. In the cold start setting, which is the first scenario, we only run the benchmark once and start with an empty QEPS that is updated after each query execution. This allows us to rate TONIC's capabilities of transferring stored cases to new queries. For the hot start setting, on the other hand, we use a warm-up phase and a pre-populated QPS that already stores all relevant cases and therefore comes with a guaranteed prefix match for all queries. Now, if we first focus on the native Postgres plans, we see a huge difference between the cold start and the hot start setting, which indicates strong caching behavior for the native plans. In particular, we found out that the benchmark execution time for the native Postgres system is dictated mainly by 2 or 3 very long-running queries. So Postgres actually shows problematic tail latencies. However, combining the optimizer with TONIC reveals a substantial speed up in both settings. First, we see that TONIC is able to transfer meaningful operator decisions to unknown cases in the cold start scenario. And second, TONIC is close to match the optimal operator selection for the hot start setting. In our paper, we use TONIC in combination with several optimizers to show that TONIC is not limited to the Postgres optimizer. For instance, we combined TONIC with the Simplicity Query Optimizer, and Simplicity is a pessimistic join ordering concept based on a simple upper bound that has been published 21 at CITER. So in particular, Simplicity seeks to avoid single long-running queries by forcing one-to-n joins before potentially expanding and therefore more dangerous n-to-m joins. And the n-to-m joins are enumerated according to a cheap upper bound. From the results, we see that Simplicity successfully avoids single long-running queries as it executes much faster in the cold start setting. And again, combining Simplicity with TONIC shows close to optimal operator selections, and therefore it becomes evident that TONIC works in tandem with any generic query optimizer. In this last experiment for this presentation, we compare TONIC to BAO, which has been published last year on Sigmod. And BAO is a state-of-the-art machine learning approach that also learns from query feedback, much like TONIC. However, instead of using a fine-grained operator selection for individual joins, BAO learns and selects SQL hint-set combinations like set enable nest loop to off or on to guide the underlying optimizer towards better planning decisions. To evaluate the learning capabilities of both approaches, we run a particular fraction of training queries and freeze the models afterwards. So in particular, the QEPS for TONIC and the neural network of BAO. With the so far trained models, we execute the benchmark end-to-end and measure query response times. As can be seen on the right-hand side, TONIC shows a very stable rate of improvement due to its white box learning paradigm. TONIC only revises operator selections when it knows that it can do better than the underlying optimizer due to a guaranteed prefix match. Vice versa, TONIC recognizes when it's in complete unknown territory as there is no prefix match. TONIC then simply falls back to the native optimizer for the operator selection. In contrast, ML approaches can be trained on a small fraction of queries and make decisions for completely unrelated queries. In particular, the black box nature of neural networks make it very hard for us to understand the decision process. This brings me already to the end of this presentation, where I hope I could give you a nice overview of our work, where we present TONIC for near-optimal operator selections. TONIC can turbocharge generic query optimizers while following a white box learning paradigm. And since TONIC directly learns from query feedback, there is no need for error-prone cardinality estimates. And further, as can be seen in the paper, TONIC is particularly fast in adapting to workload changes.